Welcome to my today's Bachelor thesis presentation with the title MATLAB Automated RF-Demonstrator for the AST Linearity Test. So in modern vehicles and in autonomous driving, advanced driver assistance systems, short ADAS, are mandatory. Some ADAS are, for example, radar, lidar, or cameras. For ADAS, there are also safety requirements which are written in the ISO 26262 standard. In this standard, so-called built-in self-tests, short BIST, are classified for monitoring the gain, the phase noise, and the linearity of a system. For the linearity, you have to monitor the third order intercept point, or short, the IP3. And for on-chip monitoring, we unfortunately only have no low-quality test signal generators. But for the conventional IP3 measurement, it is mandatory to use two signal generators with very high quality, because otherwise the nonlinearities from the test signal generator are visible in the nonlinearities from the system under test. And one algorithm or one approach is the artificial slow time, or short AST Linearity Test. It was developed by my supervisor, Matthias Wagner, and in my bachelor thesis, my main tasks are to understand the AST Linearity Test, mathematically derive it, simulate the principle in MATLAB, and then prove the practical implementation with an MATLAB Automated RF-Demonstrator. If we are plugging in a two-tone signal, like shown in this formula, with two frequencies omega 1 and omega 2, and the amplitude A0, into a nonlinear system with alpha 1 as the linear factor, alpha 2 as the second order distortion factor, and alpha 3 as the third order distortion factor, we will get intermodulation distortions at the output. Third order intermodulation products appear next to the fundamentals. In green, you can see here. And these products should be very small since they cannot be filtered out. However, second order distortion products are mostly smaller and are somewhere in the frequency band far away from the usable frequency band. And they can be filtered out this way. So the IP3 is measured according to the fundamental power P1, so the power of the fundamental, and the IM3 product power P3. This is this power here, with the according formula P1 plus half P1 minus P3. It can also be shown more mathematically, of course. You can see the fundamental, the third order harmonic, and the third order intermodulation product. Just keep in mind those factors 1/4, 3/4, because we will need them afterwards if we're comparing the AST linearity test with the conventional measurement. And it also can be seen that the fundamental is actually reduced, because alpha 3 is smaller than 0, of a small factor here. And because of this reduction, the exact IP3 value cannot be measured, not even with the conventional method. But with the AST linearity test, an exact IP3 value is provided. And also, for the sake of completeness, this is also the mathematical formula for a single tone for a conventional measurement. However, with a single tone and the conventional measurement, the IP3 is not measurable, because the nonlinear term, what is in this case the 3/4 part, so the IM3 product from the two-tone case, is on the same frequency as the fundamental F1. So if we are measuring the power of the fundamental, we cannot distinguish between the linear and the nonlinear power level, and can therefore not calculate the IP3 value. But with the AST linearity test, this is also possible, as it will be shown afterwards. So then let's dive into the AST Linearity Test. The main principle is that we are injecting a low quality test signal multiple times instead of just one time, and each time scaled with a different factor. This can be achieved with a voltage controlled attenuator or a voltage controlled amplifier. And we are scaling this with m is 8 and a cosinus with this following index. So we are getting these values here. And in fact, we just need one and an attenuation of 3 dB or inverted or 0. So it's pretty straightforward, and I will show you afterwards that this can be implemented really easy. So with n, we actually get an additional time index which is artificially introduced. And this is also called the slow time index. And d will be referred to as the fast time index. And the FFT along n is also called the Doppler FFT. And we also need a second FFT along t, which is called the range FFT. And this 2D FFT is often already implemented on FMCW radar chips, so we don't even need extra hardware for the AST linearity test. And with this sum, we can the parents affecting the test signal before the analog signal, for example, of the test signal generator, can be separated from nonlinear effects after the scaling, so from the signal under test. So we saw before the receiver block diagram, and now we can see for the AST linearity test, we just need the voltage controlled attenuator here and the processing chain for the AST linearity test. So the Doppler FFT and the range FFT. And afterwards, the evaluation, what is shown afterwards, for example, multiplying by 4. The output of the system after STEM looks like this. You now see that again with this n slow time index, we can separate because we have a cosinus with an index of 2 and a cosinus with an index of 6. So we again can separate the linear and the non-linear factor already with this index of the cosine. We can also simplify this because the 3/4 term is much smaller than the alpha 1 xt term. And now we can insert this signal 8 times and measure it out in the output. And then we get this matrix here with 8 signals and k sample values and in each column. And we can then do the Doppler FFT and the range FFT. Now, if we plug in the two-tone signal into the system with the sum, then we get this signal at the output. Now we can see that the fundamental is multiplied with the cosine and 2 pi in its index, and the third harmonic and I'm3 product are multiplied with a cosine with 6 pi in its index. So the terms involving 2 pi are mapped to the fundamental plot, and the terms involving 6 pi are mapped to the third order components plot. So if we are doing a Doppler FFT along the slow time index n, then we can separate those factors like shown on the next slide, because now we have y1 for the fundamental plot and y3 for the third order intermodulation plot. And in y1 we just have the fundamental, and in y3 we again have the third harmonic and the I'm3 product. We also get an term with 9/16, but this is a frequency out of interest because it is in the third order plot and it's on the fundamental frequencies. But that's not really interested for us because the fundamentals are in the fundamental plot. I will show you afterwards what I mean with this. But we can see that 1/16 and 3/16 must be multiplied by 4 to actually get the components, the power components as we saw before with the conventional measurement and the two-tone measurement. And then we can evaluate the IP3 value after the second FFT along T, the range FFT. So the range FFT of y1 and the range FFT of y3. And then we can calculate or measure P1 and P3 again and calculate IP3. For this, we need, of course, a demonstrator. In this demonstrator, we have the voltage-controlled attenuator, the low noise amplifier, and the mixer. Furthermore, we need a voltage supply for supplying the voltage-controlled attenuator and the low noise amplifier, and also controlling the voltage of the voltage-controlled attenuator. Then we need the signal generator, which is providing the two-tone signal, and another signal generator for the local oscillator. And then we have the oscilloscope for sampling the time domain signal and sending it to MATLAB. In order to simulate the system, we need alpha 1 and alpha 3 for this. So we measured the IP3 and gain values and also compared it with the values in the datasheet and calculated the gain by just adding up the individual gains, which is resulting into 4 dBs, and then calculate alpha 1, which results in 1.585. Then afterwards, we calculated the total IP3. So this is the cascaded IP3 of the individual IP3 of each component. But for this, the formula needs, and this is why the variables are written in lowercase, are needing milliwatts. So first, the dBm values are converted to milliwatts. Then the total IP3 is calculated with 1.731 milliwatts, and then this is again converted back to dBm. Then we have the IP3 with 2.383 dBm. This is converted to volt peak, and this is then used together with alpha 1 to calculate alpha 3, which yields into minus 30.667. Now we have the model in MATLAB ready, and we finally can simulate it. First, we want the conventional measurement with a two-tone input and no quantization noise. This obviously works perfectly fine and results into an IP3 of 2.202 dBm. With 2-bit quantization noise, we, as expected, get a wrong IP3 because now the quantization noise is overlapping the third order intermodulation distortion and the IP3 is completely wrong. So with a low quality test signal generator, the conventional measurement cannot be used. Now with the AST linearity test, with no quantization noise, the IP3 equals 2.248 dBm and is correct. And now we can see that we also have separated the fundamental spectrals and the third order harmonics. We also can look at this with the split view. We don't have a DC and a second harmonic component because alpha 0 and alpha 2 are set to 0, but we have our fundamental and our third harmonic component. And now we just measure P1 here and P3 here, and we can calculate the IP3. This is what I meant before with the fundamental component plot and the third harmonic component plot. And as you can see, we also have the fundamental spectrals here and also some other spectrums. We don't saw them in the calculation because we used the approximated formula for this. And if we are applying now a 2-bit quantization noise, then we can see that the AST linearity test is capable of separating the fundamental third harmonic and calculate the IP3 correctly. And also with a single tone input, now the IP3 can be measured because even though it's on the same frequency, both power levels can be separated into two separate views and the IP3 can be calculated. And also, of course, with a 2-bit quantization noise, the IP3 is also correct. To summarize the values, we can see, as I told you, with the conventional measurement and quantization noise, the IP3 is wrong. The values in the brackets are the results if the approximated formula is used. And Actually, if we are using the approximated formula, then the nonlinear part, which is reducing the fundamental, is neglected, and therefore the exact IP3 can be evaluated with the AST linearity test. So now the working principle of the AST linearity test is verified. That's why we can now dive into the measurement. We use MATLAB to communicate with the measurement devices, and therefore we are using the standard commands for programmable instruments, so SCPI, which are sent over Ethernet, more precise TCP/IP, with predefined and fixed IP4 addresses for every device. So one is a signal generator, which provides the local oscillator frequency at 1 GHz and a power of 10 dBm. Second is our voltage power supply. There we have 3 channels. 2 channels are outputting 3 volts for our low noise amplifier and our voltage controlled attenuator. And the third channel is used for controlling the attenuation of our VCA. And it is for 17 volts we have 3 dB, and for 5.2 volts we have 6 dB. Then we have here the vector signal generator, so our test signal generator, which is producing a single sideband modulated two-tone with the local oscillator of 1 GHz again, and output power of minus 25 dBm. 4 is of course our digital storage oscilloscope, which is measuring and sampling the time domain. 5 is our demonstrator, and 6 would be a spectrum analyzer if we're needing it for optional purposes. For example, measuring the mixer or the IP3 of the mixer or an LNR and so on. So now I want to talk about how we implemented the stem. As I told you before, we just need one attenuation of minus 3 dB and then repeating or negating them. And our first approach was to input one period for each scaling and then assign the signals smart, as shown here. But if you are Fourier transforming half period, then you get leakage, obviously. So we injected multiple periods per scaling, and then always for one factor get the whole period. For example, we have here 1, minus 1, 0.7 here, minus 0.7 here, and the zeros are just inserted into the measurement. And then if we're doing a Fourier transform here, we get nearly no leakage. And we have one further problem, because the internal LO of the IQ modulator in the vector signal generator is not accessible from the outside, and this is why an additional signal generator is used for the LO of the mixer. Hence, both LO are sometimes not perfectly synchronous, and therefore quantization noise leaks into third order components plot. And this is why the quantization noise increases with higher frequency, and also the IM3 products are therefore wrong, and also the IP3 is therefore evaluated completely wrong. Now we have our measurements, and for the conventional measurement, again, we got obviously the right dBm value. But with a 2-bit quantization noise, now the IM3 products are again overlapped and the IP3 is again totally wrong. Now it is getting interesting. Is the AST linearity test also working for practical implementation? So first, we have a look at the IP3 value with no quantization noise. Again, with 2.2, this is perfectly fine. And now we see that with also 2-bit quantization noise, we approximately get 2.2 dBm, and therefore the IP3 value is evaluated correctly. We furthermore see that the test signal generator sampling frequency is 15 MHz. So at 25 MHz, the quantization noise reduces because the signal is its end is here, and then it's decreasing to the actual noise floor of the measurement setup. We also tested the AST linearity test with a single tone input. However, the single tone input is very susceptible to voltage controlled attenuator deviation. And as you can see, with no quantization noise, we have a too high IM3 product because the fundamental power is leaking into the IM3 product because it's on the same frequency level. And therefore the IP3 is a little bit wrong. But if we are applying a 2-bit quantization noise now, then the IM3 product is kind of the same. So the single tone input would also work, but is very, very susceptible to VCA imbalance or deviation. But in the end, the AST linearity test, the practical implementation, is successfully confirmed, obviously. However, the two-tone measurement should be preferred in practical implementations, and the measurement results match very well with the simulated results. So what's the conclusion? With the AST linearity test, the IP3 can be measured exactly. The test signal generator can be of low quality, so area and coasts are saved during on-chip build. Then we can measure the further intercept point with a two-tone signal, of course, but theoretically also with a single-tone signal. And a lot of hardware of, for example, for the 2D FFD is reusable in FMCW radar transceivers. So what's the outlook now? We should analyze and tackle the impact of the deviation in stem factors. So to improve the IP3 results even more, and to tackle the LO synchronization problem, as I mentioned before. However, on integrated circuits, this LO is very synchronized throughout the whole chip, so this is not really a problem if someone wants to integrate the AST linearity test. We should increase the target frequency because now during the Bachelor thesis it was always tested with 1 GHz. We maybe should also test it with higher frequencies, for example 77 GHz, in order to see if there are other problems occurring with higher frequencies we have to deal with. And in the end, a realization of the AST linearity test in hardware would be great, because now the signal is transmitted from the oscilloscope to MATLAB and is then processed digitally on my computer in MATLAB. But it should be also tested, for example, on a microcontroller or on an FPGA. If, for example, to get the semiconductor area, the power efficiency, the timing efficiency, and so on. But all in all, this project is really promising. I really liked working on it, and it is really usable for every RF engineer and RF measurement engineer. Thank you very much for attending this presentation. I hope you learned something from it, and please do not hesitate to ask some questions. Thank you very much.